Fine. So we were discussing about this solution of this problem using finite elements, and we discretized this problem by using four two-noded elements. And as we know, the partition of domain by finite elements has to be in a set of non-overlapping domains, and the only common point or the only thing that uh, adjacent elements or neighboring elements share is the node. Uh, there are common nodes between adjacent elements, and the approximation is constructed over individual element independent of the other element. So approximation of the primary variable is constructed as an interpolation between the values of the primary variables which are as yet unknown. But considering them that the value of the primary variable at node 1 is denoted as phi 1, and value of the primary variable at node 2 is denoted as phi 2, then the variation of phi within this element 1 is assumed as a linear interpolation between phi 1 and phi 2 at node 1 and node 2. So two values, two constraints, and a first degree polynomial will have two unknown coefficients, and accordingly those two coefficients can be uniquely identified in terms of phi 1 and phi 2, and a unique polynomial can be constructed. So the polynomial approximation uh, in element 1 is defined as linear interpolation between the primary values of the two nodes of element 1, that is phi 1 and phi 2. Similarly, polynomial approximation in element 2 is defined as linear interpolation between the primary variables at the nodes of this element, that is element 2 and node 2 and node 3. These are the two nodes which define the element number 3, 2. Element number 3 is defined by nodes 3 and 4, and the approximation within element 3 would be defined as linear interpolation between variable value at node 3 and node 4, and similarly for element number 4. So that graphical representation of the mesh is encoded in numerical data in the form of numerical data. So element 1 is defined by two nodes. Node I, left side node, is numbered 1 in the global node numbering. The entire domain is divided by is there are nodes placed at distributed over the entire domain, and these nodes are numbered sequentially, so as unique identifiers, and element is defined by the nodes which comprise those elements, and the nodes themselves are identified by their coordinates. So four nodes, and they define the four elements. Five nodes define the four elements, two nodes for each element, and we construct the interpolation in this form. So this is a generic description of a two-node one-dimensional element. Ith node defined by the coordinate xi, jth node defined by the coordinate xj, and the interpolation function for ith node can be written straight away. It's a linear polynomial, so it can be written straight away using Lagrange interpolation formula, and that can be given as x minus xj divided by xi minus xj, and interpolation formula for node j would be given as x minus xi divided by xj minus xi, and that you can verify that it would be satisfying the basic condition of polynomial interpolation, that is, it should take a unit value when evaluated at its own native node, and it should vanish at all other nodes of interpolation. So Ni evaluates to unity at xi, and it vanishes at xj. Similarly, Nj evaluates to unity at xj, and it vanishes at xi. And since it's a linear variation, so the function themselves vary linearly. Ni starts from 1 at ith node and goes linearly to 0 at jth node. Nj starts from 0 at ith node and goes to unity at jth node. So you can, that's a standard equation of straight line. And the polynomial approximation, uh, as we know, I mean, the nodes are included in the domain. So whatever is the approximation that we construct over the applicable over the domain individual element, it should agree with the primary variables, values of the primary variable at the nodes of those elements. So if I evaluate it, if I construct the approximation for any generic element E defined as phi I ni plus phi j nj, then if I evaluate this at x is equal to xi, then I should get the value of phi I. I should get the value returned as phi I. So the polynomial, first degree polynomial, general polynomial is a0 plus a1x. So if I substitute, evaluate it at xi, a0 plus a1 xi should be equal to phi I, a0 plus a1 xj should be equal to phi j. And I know we know the coordinates of ith node and jth node. So this matrix is known. So if we can invert this matrix, then A0 unknown coefficients of the polynomial variation can be determined in terms of primary variables at these coefficients at these nodes. So A0, A1 can be expressed in terms of the primary variables at the nodes phi I and phi j, and then we can substitute the polynomial variation and substitute for a0 a1, and that gives us this interpolation functions by definition. So these terms, because interpolation formula requires this approximation to be phi I multiplied by ni plus phi j multiplied by nj. So these two terms have to be identical with ni and nj, and therefore that's how we get these terms. And if you calculate all these, then compute the inverse, this is what you get. And if you calculate these values, then evaluate this matrix multiplication, then this leads to the same interpolation formula that we discussed a little while back, Lagrangian interpolation formula. So the shape functions can be obtained. Shape functions can also be derived by using Lagrange interpolation. So Ni is given as negative of x minus xj divided by xj minus xi, and Nj is equal to x minus xi divided by xj minus xi. So, so just to emphasize that this we can derive these interpolation functions from the first principles, but you will realize that these can also be derived straight away by using Lagrange interpolation or other interpolation methods. So now we can look at the individual element, the what is the weighted residual statement for the domain residual in element E, individual element, right? So boundary residuals we do not worry about at the point, at the moment. We will come to that in a little while. So let us only concentrate about the weighted residual of the domain residual error in the satisfaction of the boundary differential equation in the domain. So substitute the approximation over individual element phi hat e in the governing differential equation, and integral obviously needs to be evaluated only over individual element f omega e, and wk is some weighting function. So if we develop the weak form of this weighted residual statement, then we can have one integrated by parts, and there will be this boundary term, and this derivative would be transferred to weighting function term. So dw by dx multiplied by a times d phi hat over dx plus this carries through as it is c times w times phi hat, and this is the weighting function multiplied by the distributed traction. So now we can substitute this a times d phi by dx at the individual elements, and we can find that this is uh, wi at the ith node, qi is the secondary variable, and that is given as negative of a times d phi by dx at x is equal to xi, and qj is equal to a times d phi by dx at x is equal to xj. So that is how if we evaluate all these, then this brings us to this particular form. And using Galerkin approach, now we can look at this expression phi hat is given as interpolation model. So phi hat is equal to phi I multiplied by ni plus phi j multiplied by nj. Ni and nj, they are the interpolation functions corresponding to node I and j. So weighting function, so the basis function here for the approximation of phi hat are ni and nj. So we will use weighting functions same as the interpolation functions. So once we will derive the equation by choosing w as ni, and second equation will be derived by choosing w is equal to nj. So that's the only additional feature that we need to uh, understand while adapting the method of weighted residual for this polynomial kind of approximation, polynomial interpolation approximation. So following Galerkin approach, let us first consider Wk is equal to Ni x in the weighted residual statement. So dw by dx is equal to dni by dx, and that is equal to, I mean, x minus xj was the numerator, so derivative would be minus of 1 over xj minus xi. So we multiply, evaluate, substitute that dw by dx in the weak form of weighted residual statement, and we have this expression. And d phi by dx, obviously that's going to be constant because phi hat is a linear variation, so derivative is going to be constant, and that's just going to be the difference in the primary variables at two nodes divided by the distance between two nodes. So that's what you have. This is d phi by dx, so d phi j minus phi I divided by xj minus xi. And this is of course w multiplied by phi, phi hat. So all the expressions. So this is ni as a weighting function here. This is ni phi I plus nj phi j, and this is again ni multiplied by q dx, and this will be minus qi. The other term will vanish, There are two terms here, W at xj multiplied by qj and W at xi multiplied by qi. So this term, qj term, will vanish because ni vanishes at xj. So this term will vanish when the weighting function chosen is ni. So that's how you get only one term here, that is qi, because ni evaluates to unity at x is equal to xi. So this w at xi is equal to 1, and that's how you get this minus qi term here. And once you evaluate, as you can see, this is a straightforward integration between xi to xj. No further complication. It's just polynomial. If you multiply these are just polynomial terms. This is second degree polynomial. This is also second degree polynomial. This is first degree polynomial. And this is a constant. So if you integrate these, you will get the expression like this. Evaluate these definite integrals, and you end up with these expressions, which are equation, I mean straight line, first equation uh, in terms of the primary variables at nodes I and j. So phi I and phi j. So these are the, and right hand side, I mean these load terms, we can take it to the other end, and this is equal to q times xj minus xi by 2, and this is qi would be equal to minus a d phi by dx at x is equal to xi. And similarly, substituting w as nj in the weighted residual statement will provide the second algebraic equation in the same way. And there are two equations in these two unknowns, phi I and phi j, and they can be arranged in matrix form as k times phi is equal to f. Right? The coefficient matrix Ke is referred to as the element stiffness matrix. Phi E is the array of unknown primary variables at element nodes, also known as degrees of freedom in structural mechanics parlance. And Fe is the vector of equivalent nodal forces. Now we are looking at, so this is the equilibrium statement of the forces, external forces and internal forces at the nodes of finite element model. Right? So everything is with respect to the quantities at nodes. So phi I, the phi, this vector refers to, contains the values of primary variables at the nodes of element, and Ke is the associated stiffness matrix terms, uh, which provide the internal forces in the element for unit deformation corresponding to the nodal degrees of freedom. And these are the external forces and also the uh, reactions that we will at points where the boundary conditions are to be specified. So, more specifically, the elements of these matrices and vectors for the two node linear element can be given, and we can go for a little longhand. So the two elements, diagonal elements of this are identical. They are given as this. You can verify from the evaluation of the integral. The off diagonal elements are also equal, and they are given by this. And this equality emphasizes the symmetry of this coefficient matrix K, and that is a direct fallout of the choice of, or the use of the Galerkin method for weak, weak form of weighted residual, uh, method of weighted residual. And these nodal values of the external loads, they are related to distributed fractions and the associated secondary variables at the nodes. And this is for ith node, and for jth node, as you can see intuitively what we do, if there is a uniformly distributed load, the force is distributed equally at the two ends, and that's what you get here. q multiplied by qj minus qi by 2, q multiplied by qj minus qi by 2. Total load is q times l, length of the element. So that's the total load being distributed equally at the two nodes of element. So collecting these, and now this is what we have generated for a generic element. So I can now look at element number one, and this is what you should notice. Now you can see how automatic it becomes. Once I have this generic formulation, then I just go at element one, identify what is the node I and what is the node j, and corresponding coordinates of ith node and jth node, and evaluate these expressions. And I have the complete expression, complete equation ready. So element number one, ith node is the node number one in the uh, mesh, global mesh, and node j is the node number two in the finite element mesh. And accordingly, phi I is identical with phi 1, and phi j is identical with phi 2, and xj minus xi is equal to L by 4. And thus, the element level algebraic equation for element number 1 is equal to this. I just substitute this xi is equal to 0 and xj is equal to L by 4, and evaluate those generic expressions, and you get these results, right? And these are the secondary variables at node 1 and at node 2. Secondary variable at node 2. Similarly, I can go now to the element number 2. Element number 1 is done and dusted with. So we have converted the differential equation into this algebraic equation representing element 1. Now I can go back to go to the next element in the mesh, that is element 2. And now ith node is node number 2 and jth node is node number 3. So accordingly, phi I is equal to phi 2 and phi j is equal to phi 3. And xi is equal to L by 4 and xj is equal to L by 2. And the length of the element is equal to L by 4 again. So substituting these values in that generic expression that we had derived, we can get the algebraic equation corresponding to node element number 2. And you will see that the coefficient matrix, of course, they are identical because the problem doesn't change. It is the identical problem, right? So this K11 is same as K11 or K12. That diagonal elements are identical, and the off diagonal elements are also identical. So the coefficient matrix is same, and similarly, these load vectors are also same because all elements are considered to be of same size, and nothing changes. The load distribution is same, the properties are same, everything is same. So there is no reason why we should expect anything different in different elements. So similarly, element 3 we can get the same set of algebraic equations and element number 4. Now the problem is we have been able to achieve this by virtue of constructing piecewise approximation over individual element, and now these algebraic equations, they represent the uh, they are representative of the weighted residual statement over individual element. Now the next task that is at hand is the imposition of uh, continuity requirement, or taking contribution from all of these individual elements and then combining them to get the sense of total domain, the entire problem, right? So combine element level approximations to assemble approximation for the whole domain. And this is what we uh, refer to as from part to whole. If you recall your training in surveying, so we have two approaches. First, we go from whole to part, and then we go from part to whole. And that is what we had been doing. We discretized the domain, so that was going from whole to part. We divided the domain, entire domain into subdomains. So that is from whole to part, and then after constructing approximation over individual subdomains, we now go from part to whole. So individual subdomain contributions are being will be accumulated to give us the representation for the whole domain. So this process is what we call as the assembly of equations. So we try and assemble element level equations to construct a global approximation valid for the whole domain. And this is based on the node or joint equilibrium, the concept of node or joint equilibrium. And we look at the particular case when we take the assembly of equations for finite elements of 1 and the adjacent finite element, that is 2. Element 1 and element 2, they are adjacent elements and they share a common node, that is node 2. So finite element 1 equations are defined by k1 phi1 is equal to f1, and finite element equations 2 for element 2 are defined by k2 phi2 is equal to f2. And phi 1 is the vector which contains the variables, primary variables at node 1 and node 2, and phi 2 is the vector which contains the primary variables at node 2 and node 3. So obviously you can see that there is going to be some kind of overlap because the primary variable at node 2 is common between the two sets of equations. So if we just graphically match these, so these four elements, they come from element number 1, and these two elements, they come from element number equations for the element number 1. And then the second four terms, they come from equations for element number 2, and these two terms come from the element number 2 equations. So essentially, the common terms associated with degree of freedom at node 2 or the primary variable at node 2, they are added up because all of them they depend on phi 2. So if I look at these equations, so the first row refers to k11 of element 1 multiplied by phi 1 plus k12 of element 1 multiplied by phi 2 is equal to f1 of element 1. Then this is k21 of element 1 multiplied by phi 1, and then this is k22 of element 1 plus k11 of element 2, right? So k21 plus k11 because both of them multiply with phi 2, the primary variable at node 2. And this one is of course k12 of element number 2. So I'm sorry, this is uh, typographical error. This should be element number 2 here, right? So this superscript should be element number 2. Oh, no, this is actually coming from element number 3. So this is global system, and this is only this graphical representation is only for two elements, but these equations they refer to all the four elements together. So this is fine. I'm sorry. So this process of assembly allows us to assemble the complete element level equilibrium equations in the same fashion. So when I take the equations for element number 3, there is going to be overlap at the term corresponding to phi 3. That is what you see here. Phi 3 gets an overlapping contribution from equations for element number 3, and phi 4 terms corresponding to phi 4 would get overlapping contributions from element number 3 and element number 4. And phi 5, of course, it is only contained by in the element number 5. So there is these terms would only come from element number 4 equations. So now let us look at these terms. We see there are these two terms, F2 from element number 1 and F1, the first element of the force coming from element number 2 adjacent to, because this is the jth node, node 2 is the jth node for element number 1, it becomes the ith node for element number 2. So right hand side node and left hand side node, and therefore if we add these two terms you will see F2, I mean the jth node and ith node for next element. So you have QL by 8 plus A times d phi by dx at jth node, and add to this QL by 8 minus A times d phi by dx. This is what is happening at the ith node. So these will of course add up, and they will get to QL by 4. But what it happens here is very interesting thing. The signs of these are of opposite nature, right? And they would represent like a free body diagram. The forces, if you uh, imagine a cut through the element passing through the node, then what are the axial thrusts that you will have? So obviously there is going to be an equal and opposite pair so that the system remains in equilibrium at that section. And that is what is being seen here. So these are the equal and opposite forces at the same point, and they should vanish each other. So they should cancel each other, and that's how this assembly would lead to QL by 4. Now that is the theory. In practice, if you look at it, this approximation is over element 1 and this approximation is at element number 2, and because these approximations are linear, this is d phi by dx is essentially phi 2 minus phi 1 divided by x2 minus x1, and this one is phi 3 minus phi 2 divided by x3 minus x2. So these are going to be different. Phi 2 minus phi 1 need not be equal to phi 3 minus phi 2, even if x2 minus x1 is equal to x3 minus x2. So these numerators may be different, and therefore these may not be exactly equal to 0, or these may not cancel each other. So this is what we mean by C0 continuity elements. The continuity of the first order derivative is not guaranteed. So there is going to be some difference in this first order derivative. And this difference is actually being used, is actually used to infer the quality of approximation. If this difference is too much, then the mesh is not fine enough, and we need to use a smaller size of element such that these differences are reduced somehow, somewhat. So that will answer the query that you had raised some time back. How do we decide what should be the size of finite element? How do we decide, take a call, what is a good size, good enough size of finite element? So there is no guideline, a priori, that can solve that problem, answer that question. But once you do a finite element analysis, then you look at this secondary variable, how the secondary variables balance. Ideally, they should be able to balance each other out when you assemble these contributions, but they will not in general. But even then, you should be able to, at least they should give you the trend. So what is the trend of this variation across the element boundaries? So if you are able to spot the trend, then probably that is good enough approximation. But if these variables are too way off each other, then there is scope for further refinement. So we will assume that these are almost negligible. This summation, this combination of these two terms is negligible as it should, and this is approximated as QL by 4. This we ignore this term. And first term, because it only includes this one term, there is only one ith term here, so this is what it is. And if you recall, there is a phi prescribed there, so this value cannot be prescribed. This is secondary variable, and this is what is you will realize that this is the reaction of the support, and this is what you obtain as a post-processing solution as a reaction. And at node number 5, you will find that again you have this expression, and that is given as a natural boundary condition of the problem that a times d phi by dx at x is equal to L is equal to q0. So you just replace this by q0, and the forcing function at node 5 is equal to ql by 8 plus q0. So with that, uh, natural boundary conditions have been taken care of. This boundary condition specified in terms of the secondary variable of the problem that has been taken care of. And now we are left with the total assembly, and the essential boundary condition phi 1 is equal to phi hat is to be uh, phi 1 star, whatever that value is, uh, that needs to be specified, that needs to be incorporated in the system of equations. So now we look at this system. I mean, if we have to specify phi 1 is equal to phi 1 star, phi 1 star being some constant value. So let us look at the first row of the equation where the phi 1 is the diagonal term. So k11, we write this k11 phi 1 plus k12 phi 2, there would be some other terms, is equal to f1. That is the equation. So what we do here is we add alpha times phi 1 here in the diagonal, and alpha times phi 1 star, that is the value that is to be prescribed. So phi 1 is to be prescribed as phi 1 star. And alpha is a constant which is much larger than any of the terms here, any of these coefficients k11, k12, k13, etc. So maybe 10 raised to the power 5 times larger than this. So what happens when you have this? So this is similar to attaching a very stiff spring of stiffness alpha at that degree of freedom, phi 1, right? So if the stiffness of this artificial spring alpha is assumed to be very large, let's say of the order of 10 raised to the power 4 or 10 raised to the power 5 times the largest stiffness coefficient in this row, then this equation can be approximated. Now imagine alpha is a very large quantity corresponding compared to all of them. So this can be represented as alpha times phi 1 plus some negligible terms, and f1 is also going to be negligible in comparison with alpha times phi 1 star. So alpha times phi 1 plus negligible terms is equal to alpha times phi 1 star plus negligible terms. And when you solve for these, you can drop these negligible terms. When you solve for these, you will get phi 1 is equal to phi 1 star. And that's how the boundary condition on essential boundary condition on the primary variables are prescribed, are imposed. So once this task is done, the system of equations can be solved, and the entire problem, rest of the unknown variables, phi 2, phi 3, phi 4, they can be computed from this system of equations k phi is equal to f assembled system of equations. And that will complete the solution of uh, problem, entire problem. And if we wish to find what is the axial thrust, then we go back with these individual element nodal deformation, primary variable phi 1, phi 2, phi 3, phi 4 that have been computed as a process of this solution, algebraic solution. We can go back to element level equations, substitute phi 1, phi 2 or phi 2, phi 3, phi 3, phi 4 or phi 4 and phi 5 in individual element level equations and determine what are the secondary variables if we wish to find what is the axial thrust or secondary variable in the individual element for our design calculations. So that completes the discussion of uh, this simple problem of solving this rod problem by using finite elements of C0 continuity. Now, of course, this element is same element which is used for analysis of truss problems, two-dimensional planar trusses, and also uh, three-dimensional trusses as well. The only thing that needs to be uh, done here additionally is to account for the fact that the elements can be in arbitrary orientation. So the element E can have an orientation with respect to the coordinate direction. It need not be aligned with respect to one of the coordinate directions. So for example, element E is oriented with respect at an angle theta from x here in this particular example. So what is done here is obviously it is easier to formulate the element level equations and all the formulation with one of the coordinate axes oriented along the element length. So now we use uh, two systems of coordinates. One is local coordinate system and one is the global coordinate system. So global coordinate system is what the problem is specified in terms of this global frame of reference. But when we generate the element level equations, we work with the local coordinate system and generate equations in terms of these local coordinate system, and before assembly we transform the equations into a global frame of reference so that all the element level equations they are referred to same frame of reference before assembly, and rest of the process is same, exactly same with what we have done earlier. So it is convenient to formulate element equilibrium equations with coordinate directions oriented along a member, and that is referred to as local coordinate system. And different members might have different orientations in a structure, and it is necessary to transform the element equilibrium equations to a common global frame of reference before the assembly of equations. Right? So this is something that probably all of you have already uh, handled, already done with during your matrix methods of analysis. So it should be pretty straightforward. Just look up the uh, relevant examples, and things will get clearer when you solve some problems in the next assignment dealing with these issues. So that's all for today. If you have any questions, please feel free.